Now there are some theorems which we can use while solving some limits. Now it says, if fn is a sequence such that limit n tends to infinite, fn+1 upon fn, it is equal to L, where mod L is less than 1, then limit n tends to infinite fn will be 0. And if this L is greater than 1, then in that case, fn, it diverges to infinity. Now let us take up an example. Say for example, show that this limit n tends to infinite, 2 to the power minus n into n square, it is equal to 0. Now what we'll do is, we'll write fn as 2 to the power minus n into n square. Now fn+1 upon fn will be 2 to the power of minus n+1 into n+1 square upon 2 to the power minus n into n square. Now 2 to the power minus n will cancel, so we can write this as n+1 square upon 2n square. Now we take this limit n tends to infinite, this limit will be simply 1 by 2, and which is less than 1. So if mod L it is less than 1, then this limit n tends to infinite fn will be 0. That means this limit n tends to infinite fn, which is 2 to the power minus n into n square, will be simply 0. And this is how we prove such questions. Now here the question is, show that this limit n tends to infinite m-1, m-2 up to m-n+1 upon factorial n into x to the power n is equal to 0 if mod x is less than 1. Now suppose this is fn. We'll find this limit n tends to infinite fn+1 upon fn. Now fn+1 will be this limit n tends to infinite m-1 m minus n upon factorial n+1 into x to the power of n+1 upon m-1 m-n+1 upon factorial n. Now here all these terms, they'll cancel. So what we'll get is, we'll get this as limit n tends to infinite m minus n, here we'll also have x to the power n into x upon n+1, and if we divide it by n, we can write this as limit n tends to infinite m by n minus 1 into x upon 1 plus 1 by n, which is nothing but minus x. Now this is your L. Now value of this limit will be 0 if mod L it is less than 1. That means mod of minus x will be less than 1, or we can say when mod of x is less than 1, which is what we need to prove.